Welcome back to Who Gives a Sheaf. Today's episode is probably going to be a long one. We're going to make use of some tools from the previous episode. But the big idea is this. We're going to talk about functors between categories of sheaves. So what do I mean by that? I mean, if we have a topological, continuous map of topological spaces, we have our categories of sheaves on either of these topological spaces. And so naturally one might wonder, if I have a morphism that relates these two topological spaces, perhaps there's some way that I can relate their categories of sheaves as well. So we're going to start today with sort of two classic ways to make those relations. And in fact, these are also going to form an adjoint pair. So we're going to spend a bunch of time trying to prove things are adjunctions. So the first one is pretty easy. There's a what would be called the direct image functor. So that's going to go in the forwards direction. So we call it F lower star. It's like a push forward. And we're going to map between these two categories of sheaves. By the way, this is defined as well on the level of pre-sheaves. Pretty much all the functors that we're going to talk about are. Of course, we can always just forget down to pre-sheaves, right? So in this case, how are we going to define it? Well, suppose that I have some sheaf F on X, and I want to define what the push forward is on some open set U of Y. Well, I know that F can eat, so fancy F can eat open sets of X. So what I could do is simply define it to be, since F is continuous, little f, the map is continuous, I know I can plug F inverse into there. And that's it. It's really that easy. And then what are my sheaf morphisms going to be? Well, if V is a subset of U, then of course that means that F inverse V is a subset of F inverse U. So my restriction map for the push forward at V, I can simply define it to be the restriction of F down to V. So I'm not using the superscript here because I'm sort of using the superscript to keep track of which sheaf we're talking about. I'm going to do that throughout this video, and hopefully it's implicit which section over open sets we're restricting from. So restricting down to V. That's how it's going to work. Oh, V inverse. My bad. It should be V inverse V. Yeah. So I'll leave it to you to verify that this is a morphism of sheaves, because that shouldn't be too bad for you to handle on your own. Like always, please yell at me in the comment sections if you want me to make more detailed explanations on anything I ask you to do yourself. If you're struggling with it, do let me know. But also, what is it going to do on morphisms? I have to describe this functor on morphisms. Well, that's also pretty straightforward. So F lower star of phi evaluated at this open set U, as you might imagine, this will just send it to phi at F inverse U. And there we go. There we have it. That will preserve sheaf morphisms as well. So I'm going to do a lot of things in detail today. So, you got to do some things on your own. So why is this a sheaf? That shouldn't be. This is also straightforward. Maybe I'll just say a word about it. Suppose U alpha is an open cover of some open set U and Y. And of course, suppose that we have some family S of alphas, and these are in, I guess, the push forward of F over U alpha. But that is, of course, the pullback of u alpha f at that pullback. But then also, so such that, I suppose I should also say such that, S alpha restricted to u, I'm going to be lazy, instead of writing the intersection, I'm going to call it u alpha beta is equal to S beta, u alpha beta for all alpha and beta. Well, in that case, notice that the F inverse u alpha, these form a cover of F inverse of u. But now we have a cover of F inverse of u. Oh, I should say, sorry. By the way, so important thing here. Here's where we need to be keeping track of these restrictions. So when I'm writing this, I'm supposing that I have these restrictions over in the direct image sheaf land. But if I unpack what this statement says, it says that S sub alpha restricted to F, S sub alpha using the restriction map of F inverse alpha beta, again I'll write the intersection, is equal to S sub beta F restriction map of F inverse U alpha beta, right? So I'm using that key feature here. So of course, and we're going to use this again later in the video, I'm using the fact, I'll write it out more explicitly, I'm using the fact that the inverse image of the intersection is the intersection of the inverse images. That's going to be an important tool for us. So what does that mean? Because I know that F is a sheaf and I have this compatible family, right? I know that, so hence there exists a unique S in F of F inverse U, but that is F direct image of U, such that S restricted in the sense of F restricted in the sense of F to one of these sets of the cover is equal to S sub alpha, but of course this is exactly S now restricted from the perspective of the direct image sheaf down to U alpha. So that really does tell us that the direct image sheaf is a sheaf. Pretty straightforward, pretty straight push forward, you could say. Now for the opposite direction, we're first going to define the inverse image functor. First, I'm going to define instead. So again, we've got as our setup, F is some continuous map. I'm going to define first a map just on the categories of pre-sheaves. So I'm just going to talk about it on the level of pre-sheaves first, which is fine because we can always forget a sheaf to a pre-sheaf. And here's what I'm going to do. So now let's think about this in the same way. So suppose I have some some sheaf fancy F, but now this is on Y. And I need to take F, I need to say what this is going to do to an open set of X. The problem is, now, of course, the natural thing, so if we go in the other direction, before we were able to pull back open sets. But F may not be an open map. So if I take F and apply that to U, I can't plug that into F because that may not be an open set anymore. But what I can do is instead take the limit of those open sets which contain F at U and apply and then look at those sections there. And so now this defines a pre-sheaf where what are my I wrote both as W there. So yeah, what are my restriction maps going to be? Well, if V is contained in U, then F at V, F of V is contained in F of U, and so therefore, if I had some pair in this equivalence class, WS, So maybe I should be a little more specific. What is this equivalence class, right? So W1S is equal to W2T if and only if. So notice that if W1 and W2 both contain FU, so will their intersection. So these are equal if and only if. Rather, if and only if I can find a subset of their intersection. Let's say, there exists some subset living in between the two of these, and of course also containing the image of FU. So Z is open, of course, such that S restricted to Z is T restricted to Z. Right? And there we go. So what are our restriction maps going to be? Well, notice that if I did take some subset V of U, then if I take my W that contains F at U, certainly it's still going to contain F at V as well. So basically my restriction map for some WS, so this will be restriction from the perspective of the inverse image sheaf down to V. So I'm going to drop this notation later, but so this is sort of the equivalence relation with respect to U. So now we just it becomes an even weaker equivalence relation. I just define this to be that same pair, W and S, but now it's going to be equivalent with respect to V. Okay, that's a lot of crazy stuff, and we've only just almost finished defining things. And then so finally, how is this going to act on morphisms? Well, if I have some morphism of sheaves, F from F to G, then, for any, so let's suppose we have some V which contains F at U, then phi V will be a map from FV to GV. And so therefore I'll get a map between these limits. So lim of V containing FU FV to lim, I don't know, call it, I don't really need to change the index, but to GW, let's call it. And what is that map going to do a little more explicitly? So F inverse phi over U is going to take this pair VS, and I'll simply send it to the pair V phi VS. Okay, so I'm already going to do a whole bunch of equivalence relation verifying in this video, so I'm going to leave the verification of this equivalence relation to you, and I'm going to move on to bigger and better things. Now, I've only defined a functor on the level of pre-sheaves. I now want to define a functor on the level of sheaves. So I'm now simply going to define the inverse image functor. So we might call it FP because we sort of think of it as a pullback, but there's reasons why we don't use the F upper star. We'll talk about that when we get to OX modules. But I'm going to define this to be the composition. So FP will be the composition of sheafification. So that's already a functor by our previous video, and we know how it works on morphisms and objects. And I'm going to compose it with this. So, in particular, technically, if I start with a sheaf, we might have to start with our forgetful functor first. Then we can apply this inverse image functor F-1 on the level of pre-sheaves, and then we sheafify. The reason we sheafify is because this thing I've constructed with taking these limits, this does not define a sheaf. I didn't I was too lazy to write down a very explicit example, so I'll challenge you to find your own. But yeah, the point is, if you just trust me, bro. It doesn't define a sheaf. Of course, like literally anything you want to be a functor. If you're worried that what you don't get at the end is a sheaf, if as long as you can verify it's a pre-sheaf, then you could always just sheafify, right? Because the object that you get out at the end of the day, we already know is, if your thing was originally a sheaf anyways, the thing that you get out after sheafification is isomorphic to the original sheaf. So you could just always sheafify everything all the time just to be safe. Like that movie, Everywhere All at Once. Sheafify everything all the time. That's my favorite movie. Okay, so the big result that we're after today is that for a continuous map, we have an adjunction. So an adjunction on the level of sheaves. So an adjunction between FP of, let me write G here, F, these will be sheaves over on Y, and this will be G, direct image F. So this is the big result that we'll be chasing for the rest of the video. And the strategy that we're going to use here is by using the sheafification forgetting adjunction. So this thing here, this is the same as right. This is just sheafifying. So here I've got F inverse on the pre-sheaf level, sheafifying, and here is F, and so that is going to be naturally isomorphic. I mean, forms, we already know that we have an adjunction where now this is happening on the level of pre-sheaves to the inverse image G, and okay, this is F, but like F, I'm not even going to write the forgetting, right? Or maybe I should write the forgetting, but it's just forgetting down to F, right? So now we just have the statement on the level of pre-sheaf. So meanwhile, so this is the thing in question here. So meanwhile, on the other end of things, well, what should I say? How did I write this down? Right. Meanwhile, on the other end of things, this part of it is just straight up equal, because remember, we defined morphisms of sheaves to just be pre-sheaf morphisms. So this set is literally equal, and so therefore naturally isomorphic in all, naturally isomorphic, because it's just like straight up equality. So to establish this natural isomorphism, it would actually be enough to establish this natural isomorphism, this adjunction, purely on the level of pre-sheaves. So we actually care about the sheaf version, but we're going to do this purely on the level of pre-sheaves. It's just I found it a little bit easier. So, okay, what are we going to do? I forgot to mention at the beginning of the video, which would probably help retention and engagement. I had a very hard time finding the proof of this adjunction anywhere on the internet. Everyone's always like, oh, take the natural map, take the natural map. What is the natural maps to take? I mean, okay, yes, you can say it's sort of obvious if you just think about it and sit down and write it out, but kind of annoying that there's just no clear exposition on the internet. So I'm filling that void, and I probably should have said that at the beginning of the video. Oh well, I'm too lazy to even edit it, probably. We'll see. This will magically appear at the beginning if I'm not too lazy to edit it. Okay, so first, what we're going to do, I'm going to define a natural, so we want this to be like a natural bifunctor, basically. So we want this thing to be a bijection. I'm going to actually construct an explicit inverse map to this. I will show the naturality condition for phi. I will not show the naturality condition for capital psi, its inverse. I'm going to leave that to you. Again, complain in the comments. Maybe I'll make another video about it. But I mean, it's going to be quite a bit of work to do this part already. So I think you'll be able to get it with me holding your hand through this part. Okay, so what do we need to do? So suppose that I have a sheaf morphism little phi from the inverse image of G over into F. And suppose that I have some open subset V of Y. And I need to define the sheaf morphism somehow. So I'm going to suppose that I have this S that's in GV, right? And I'm trying to define a map from G into the direct image of F. How could I possibly build such a thing? Well, let me just go ahead and define it. So I'm going to say capital phi of little phi at V applied to S is going to be, well, we have to think, how can I possibly construct it? Using this map? Oh, I think I forgot to include this explanation for why it is what it is, but maybe I'll just write it down first. So it's going to be phi at F inverse V, right? Because remember, this is a morphism happening over on sheaves over X. So I'm going to pull V back to there. I'm going to plug this in, and I'm going to apply it to the pair VS. And that's what I'm going to do, right? So why does this work? Well, when I pull back V, right, this gives me an open set. If I pull back V, this gives me an open set on X. Phi is a morphism of sheaves on X. So I can plug in my phi inverse V. I can plug that in somewhere here, right? So my phi of phi inverse V, this is going to be a map from phi inverse G at phi inverse V into F of phi inverse V, right? But remember, I'm trying to create something that's going to land in the direct image of F at V. And F at phi inverse V, this is by definition the direct image of F evaluated at V. Okay, so I've got the right kind of thing to begin with, right? But now I need to somehow use this element S and this open set V to somehow produce something in here that I can plug into this map, right? But this thing is what? It's the limit of all W which contain F of F inverse of V as I range over GW, right? And so certainly, I mean, it's just basic set theory. I'll leave it to you to verify for yourself. Just elementary set theory proof. Certainly, V does contain this set, and so therefore, this pair VS this is a well-defined class. So I really can make this definition. Great, and so this should now be a morphism. This should be a morphism in the target set here. Why don't we verify that it is in fact a morphism of sheaves? So to that end, suppose Z was some subset of V, then it will also be the case that the inverse image of Z is a subset of the inverse image of V. And so now we begin our hefty verification here. So I need to check that this map plays well with restriction maps, right? So big phi of little phi at V applied to S. And now I take the restriction map with respect to the push forward down to this open set Z. Well, this is phi, by definition, this is phi of V inverse of VS and now restricted down to the inverse image. So it's the restriction map of F, by definition, of the inverse image of Z, right? That's just from our definition. But now phi is a sheaf morphism, and I know that F inverse Z is a subset of F inverse V, so this means I have a well-defined inverse map, or rather, because this is a sheaf morphism, it's compatible with the restriction maps. And so this is going to be phi of F inverse Z at VS restriction map of the inverse image of G at the inverse image of Z. Right? So that's just by the fact the phi we started with was assumed to be a sheaf morphism. So we know that we have that. But again, remember, it's basically just, now I'm being glib with which set of equivalence classes. I mentioned this earlier that I would be. But this is basically the same as just taking the equivalence class, but now with respect to F inverse Z of VS, right? Like I defined it up above, it's just we take that same pair, and now the equivalence class is just broadening, really, or rather, more things are being identified than previously. But notice that this class, right, VS, is going to be, that's the same class as if we restrict it. I mean, if we take S and restrict it to any subset of V, by the equivalence relation, that determines the exact same equivalence class. So this is going to be phi of F inverse Z of Z S restricted with respect to G's restriction map of Z. But now what is this? I mean, this is just big phi of little phi at Z of S with respect to G's restriction map sub Z. And that, having completed, so knowing that this thing is equal to this thing up here, this is exactly what we needed to verify to know that this is a morphism from G to the direct image of F. Okay, so we've completed one direction of our map. I'm now going to construct the inverse map. Mind you, I think, do we even need, if I prove the naturality of capital phi, I don't think we even need the naturality of capital psi, because we just need that it's a natural bijection in both components. And so once I have the naturality of phi, I have the naturality, and constructing the inverse image psi on each component is basically what gives me the bijection. So so that is A-okay. So I think we're good. Okay. Now we're going to construct the map going in the other direction. So capital psi is going to go from HOM. I'm going to drop my subscripts because I'm getting lazier by the minute. It's going to go between these two HOM sets. And gosh, okay, so what do we need to do for the setup? So suppose I've got some lowercase psi, which is a morphism from G into the direct image of F. And now I want to suppose that I have some open set in X, right? Because I'm trying to define a sheaf morphism over here. And I'm going to take some section, so that's really an equivalence class in this limit of things over F of W, GW, right? Because this is exactly something in the sections of the inverse image of G over U, right? And that's the place I want to start, and then I want to end up with something in fancy FU, right? So that's what I'm after. How can we define this map? Well, So this is the thing that I'm starting with. So I know because of where S lives, right? Because of where S lives, I know that I can take psi sub W, right? Because that starts me from GW, and I can apply that to S. And that's going to be a thing that's living in the direct image of F over W, which is to say F over the inverse image of W, right? I know that thing is in there. Moreover, we also know this. This is just another more basic set theory for you to verify. Because I've taken W containing F of U, I know that F inverse W contains F inverse Fu, and I know that that contains W. So that means because my psi WS is in here and U is a subset of that open set, I can perform the restriction map down to there. So that means if I take psi sub WS and I restrict that according to F's restriction down to U, this will be something that lands in Fu. And remember, that's exactly what I was trying to construct. I was trying to start with I underlined the wrong thing there. I was trying to start with something in the inverse image of G over U and end up with something in Fu, right? So at least I've got something that is a function. Well, almost. We need to check well-defined. Let me make the definition a little bit more concrete. So here's how I'm going to do it. I'm going to define psi of psi over U. I'm going to define it to act on this pair WS. It's going to act on that pair to be psi W S and then restricting down to Fu, right? I just convinced you this thing should at least land in the alleged codomain that we're aiming for. So now we need to see that this is well defined. So, and I see now I wrote the proof wrong in my notes ever so slightly. I mean, I just restricted to the intersection, but it's I need something a little fancier than that. So suppose I've got W1S and W2T. Those are equal, so that means we can take an open set which is contained in the intersection, but of course still contains the image of F such that S restricted to Z is equal to T restricted to Z. According to G's restriction maps. I should probably be specific for the purposes of this proof, right? And now we're gonna try and make this proof go through. Boy howdy, we gotta so we're trying to prove that this is well defined. So psi at little psi at U applied to W1S. Okay, ready? Let's go. So by definition, this is psi at W1 applied to S, restricted according to what F thinks at U, right? But now this is the same thing. Gosh, I'd better be careful. This is the same thing as restricting first down to well, let's see. So let me bring this back up. So again, because of this chain of inequalities here, we know that we have F inverse of this intersection, which by the way is again the intersection of the individual things, and we have F inverse Z, and that's containing F inverse Fu, right? So because we know that we can composition of the restriction maps, we can compose restriction maps, and that composition should be associative. We know that this is going to be, maybe I should write it more in this direction because I'm going to use a lot of space. we know that this should be psi of W1 S, where, so let me write it as F restricted to Z. So first we restrict down to Z, and then we restrict down to U, right? Because we also have this this part of the inclusion there, right? So again, this gets a little bit shaky because I'm not keeping track of the set I'm restricting from. So bear with me here. But now, this should be F inverse Z. My apologies, F inverse Z. So now this is the same thing as psi sub W1 S of the restriction of the push forward of F down to Z, but then again we restrict, after that we restrict down to U. But this thing is what? Well, we know that we know that psi is a sheaf morphism, right? It's a sheaf morphism. We started with a sheaf morphism from G to the direct image of F. So we know that that has to be compatible with the restriction maps of those things. So this is going to be psi of Z of S, taking the restriction map of G and restricting down to Z. And then outside we still have this restriction down to U. But now, of course, we've assumed, right? We've assumed that these things agree. So now this is psi Z of T restricted from G's perspective down to Z. Outside I still have the FU. But now I'm basically just going backwards through all of these steps, right? Like this is going to be psi of W2 applied to T restricted from F's perspective of F inverse Z restricted from FU. That is, this is just psi W2 of T restricted from F's perspective to U, which is exactly, let me write it here, big psi of little psi of U at this equivalence class. There should be W2 and there should be T, sorry. Yeah. And so, okay, this is well defined. We just finished the verification that this map is well defined. Fantastic. Okay, so what are we doing now? We need to check that this is a sheaf morphism. There's no end to the amount of things that we need to check, but boy howdy will this series presumably pick up after this and move at a faster pace. Or maybe I'm lying. Maybe I'll keep doing these very basic proofs in gritty detail. So suppose we've got a subset, an open subset Z of U. Now I want to investigate what happens when I take psi of little psi U and I apply it to WS, and I take the restriction of F down to Z. So remember, this thing that we've constructed, it should in fact be a morphism. It should be a morphism from the inverse image of G to F, right? So those are the compatible restriction maps that we're checking. So taking this, well, by definition, this is psi WS restricted from F's perspective down to U, and then restricting down to Z. But of course, that's just psi sub WS restricted from F down to Z. And of course, that would be the same thing as if I took psi at Z and applied it to this equivalence class. Except now, again, remember, we're using the fact that, like, if I have this equivalence class and I took some W that contained the image of FU, it's also going to contain an image FZ. So technically, this equivalence class I'm writing down here is perhaps somewhat wider, more things are identified than the original equivalence class. But this is the compatibility of restriction maps. I guess I should say like this is, but I mean, again, from our definition, like that is exactly this restriction. Is it just widens the amount of things that are equivalent to it? Okay, so let me scroll back up again here. I'm sorry if it makes you dizzy. So we've constructed what I'm claiming is an inverse map to our phi, right? So I'm claiming ultimately that we have this, that I've got this sort of natural isomorphism. So I need to know that this is a bijection, right? This psi that I've defined at least is a bona fide map going the other way. I need to show that these are mutually inverse. And then I should also convince you that it's natural in all components, right? It defines that big commuting diagram. So we're not using the method of units and co-units as we did last time. Why? Well, that's because I tried to sit down and use the method of units and co-units. And I found myself a little confused, and I found this to be the easier, if perhaps more tedious, perspective to verify in very gritty, nitty-gritty detail. Okay, so now we just have to do a routine calculation to verify that these maps are inverse to each other. So we've got psi phi, uppercase, applied to some little psi at u, applied to some ws. What is that going to be? Well, just unpacking definitions, unpacking the definition of psi. We're going to have our uppercase phi of w applied to s, and then we use f's restriction map down to u. But that is using the definition of big phi. That's phi at f inverse w applied to ws. And of course, we still have this restriction down to u outside here. But remember that f is the phi that we're starting with, is in fact a sheaf morphism, and therefore it's compatible with these restriction maps, and so this becomes phi u of ws, and now we apply the restriction map of the inverse image of G to the set U. But again, as we've used several times, this is kind of just this like I mean, this is going to be the exact same thing. The thing that we get out of here would be the exact same thing as applying phi u to ws, because again of just this fact of the restriction map just being this making more things equivalent. And so, that should have been a little case, a lowercase phi. Right? And that's exactly what we wanted. Like, we wanted to compose these things and find out that we get the same sheaf morphism back. And we did by testing that on some arbitrary element. And likewise, the converse direction is also pretty straightforward. How do we do that? I mean, it's kind of plug and chug at this point. So we just take this composition, apply it to psi, apply it to some open set of y, and apply it to some s. What is that going to be? Again, we just unpack definitions, right? So this is going to be psi. By the definition of capital phi, it's going to be psi f inverse v of vs. Now using the definition of capital phi, that is just going to be psi of v at s, where we then apply the restriction map of f to f inverse v. But of course, this is psi sub vs, where now we've applied the restriction map of the direct image of f at v. And then finally, psi remember, if we're doing the compositions this way, that means that psi was a morphism from G into the direct image of F. And so again, we can just use compatibility of restriction maps, but actually look, this is already on the level of V, and so we're just restricting down to V. Nothing happened, right? This is just psi Vs, and that's again exactly what we wanted to show, that composing both of these maps gives us the identity. Okay, so the final thing that we need to do to verify the adjunction is to simply verify the naturalness of the commuting diagram. So we want to check that it's natural in both the first and second components. So for the first component, remember, so I'm going to draw the diagram that makes it look covariant, but actually remember this first case, we have like a contravariant diagram. There'll be a flipping of the diagram. So what I mean is, if we track through like how the Hom functor works, this should be well. Let me just write out the following diagram. So we need to verify the commutativity of this diagram. We've got our map psi up above, the map down below. So here we're going to apply our inverse image functor everywhere, right? And then we need to take post composition because we're applying a contravariant Hom, right? So this would be Hom F inverse G F. Maybe I should explain myself a little bit, right? When we, yeah, I guess we're applying this morphism, right? And then we're taking contravariant Hom, so we're taking Homs into F, right? And so naturally, if you have a Hom into F, you get a map that takes a Hom from the inverse image of H into a map from the inverse image of G to F just by precomposition, right? So, okay, I don't know if that one little explanation made anything more clear, but so over here we're going to have a Hom G direct image F, but over on this side, this will be a precomposition with eta, right? Because here we've just got G and F, so we haven't applied the inverse image functor here yet. And then this map down here, this is also phi, but I'll call it maybe phi prime. So in the previous video, I think in one of the videos on adjunctions, I called this thing theta, and we had theta with two components, but maybe to just keep the notation less cluttered, this would be like phi HF, and this would be like phi GF, right? But I'm just trying to keep the notation a little less cluttered. Okay, so let's just go. So again, this is just going to be some pretty straightforward formal verification. We just need to go both ways around the diagram, right? So way number one is I'll first apply phi to some little phi, so we're going this way around the diagram first, and again we're just testing this on every open set, right? So I need to see what the map is that I get when I go from GV to F inverse V, and so I'm going to take some arbitrary V, which is an open subset of Y, and I'm going to take this little test section in GV. What do I get? So simply unpacking this, this is just going to be big phi at V composed with eta V at S, but that is simply going to be putting it over here. Well, unpacking my definition of big phi, that is psi at F inverse V of V eta Vs. But of course, this is phi F inverse V. And now we've applied inside, we've taken the inverse image of the map eta at F inverse V and applied this to VS. So I guess maybe for that part, I'll just point you back to the definition of where we defined, like this was how we defined what the inverse image does on the level of morphisms. So we've got both of those. Where are we here? Yeah, but what is this? I mean, this is simply the composition of phi with the inverse image of eta, all happening at f v to vs. But what is that? I mean, that is exactly the precomposition functor of f inverse eta applied to psi at f inverse v vs. And that is exactly, going back and unwinding the definitions, that is exactly phi prime composed with the precomposition functor, all applied to phi at v at the section S. And so now if we scroll up, we can see that that's exactly what it means to go around the opposite direction of this diagram. Therefore, it's natural in the first component. And to finish our proof, we need naturalness in the second component. So again, let's start with some eta from F to H. And of course, that means that we also get an F push forward eta between the push forwards of these sheaves. Well, pre-sheaves, actually. Remember, everything here, we're doing the pre-sheaf version now, technically, as a means to prove the sheaf version. So now the diagram whose commutativity we have to verify. Again, so we're taking this map and we're now applying the covariant HOM of F inverse G into it. So I'm going to have F inverse G, F inverse G, F. The map down here, because it's covariant HOM, it will be post-composition HOM of F inverse G, H. Over here, we still got our map phi. We've got HOM F inverse G, H. Down here will be our, this should be, I made a mistake. This will be the push forward of F, my apologies. Down here will be F inverse G push forward of H. And this will be F push forward of eta post composition. And then, like before, I'm gonna call this thing down below phi prime. So we need to verify. Again, I'm gonna go this way around the diagram. So to verify the commutativity of the diagram, I've got a phi from F inverse G into F. That's my starting point. Have I done something very silly? I've done another very silly thing in my diagram. These shouldn't be here. And I'm trying to see the resulting morphism I get here. So I need to take some open set. V in Y again, and I need to take some section S in GV, and I need to see that it lands in the direct image of H. Or rather, it does land in the direct image of H, but I need to verify that both compositions work out. So one last routine calculation. We're going to have, so we're going to compose with the post-composition of the direct image of eta, and we're going to compose that with big phi of little phi, evaluate it, so testing what that does at V, and plugging a particular S into that. So that's one way around the diagram. So that is F, so that's post-composition here with phi F inverse v of vs. And that is just f push forward eta v composed with phi f inverse v at vs. But the definition of the push forward functor told us that this should just be eta at f inverse v composed with phi of f inverse v at vs. But that, of course, is just the composition of eta and phi at f inverse v vs. And finally, indeed, we can see that this is just theta prime composed with the post composition of eta applied to phi at v at s. And that's exactly what we wanted to verify. Okay, so putting that all together, right, we verified this at the level of pre-sheaves, but using our naturality argument via sheafification and the sheafification forgetful adjunction, we can actually go all the way back to the beginning here. And this natural bijection allows us to conclude that, in fact, at the level of sheaves, now we've completed this cycle, and we now have this adjunction on our hands. Okay, so that basically does it for this video. I guess there's one little other thing I did. I lied to you a little bit. I didn't fully prove that these are functors because I didn't show that they respect composition, and I didn't show that they respect identity. But of course, you're welcome to do that on your own, or ask me in the comments if you'd like to see it in detail. So now that you have even more adjunctions on your hands, you can go and try and prove a whole bunch of crazy things with sheaves. So have fun with that.